Okay, so in this video, I thought we would just go ahead and kind of walk through the actual insertions into a red-black tree. In the last video, we went over all of the different cases you could run into when you're inserting something, and there was a lot of stuff going on. So the best way to really get a handle on this is kind of walk through these different cases step by step, and then we'll really see how everything kind of ties together in order to apply these rules and really keep our tree balanced as we're adding nodes. Right, so what we're going to do is we're basically going to start off with this tree right here. And the first thing we're going to do is we are going to basically just do a nice little insert 2 into our tree. And we're going to see what happens. Right, so we insert 2, our new tree, after we insert it normally with the binary search method that we've used before, is it's going to look something similar to this. And hopefully everyone will be able to understand what I'm trying to draw out because my drawing skills are very lacking. This is why I went into computer science and not art, which is probably for everyone's benefit. Right, so we add 2 to the tree, and of course, just like every other node in a red-black tree, it will have 2 children leaf nodes, which are, for the most part, just null. Right, so after we insert 2, what we can see here is we've not broken any of our tree rules. The black height is going to be the same across the entire tree. We added a new red node, and its parent is black, so nothing changed there, and we don't have to do anything, which is really good and simple, right? So let's go ahead and we'll move on, and the next thing we're going to do is we will go ahead and just insert 3 into this tree. And what we're going to be doing here is just continually inserting sequentially larger numbers, just to show you that in the case of a normal binary search tree, if we did the same thing, we would just end up with a linked list. But by following the red-black tree rules, we're going to end up with an actually fully balanced tree as we go through inserting things. Alright, so if we insert 3 into this tree, I'm just going to copy paste this. Oops. Hopefully, to save everyone the pain and suffering of watching me draw it, but maybe it would be easier since I'm apparently really bad at selecting things. Bring you over here. If we insert 3, our 3 node would simply go down here. Of course, whenever we insert a new node, that new node is always red. So we insert 3 with its 2 null children. And now right away you can see we have a problem, right? Because this is no longer a valid red-black tree, because we have a red node or a red parent which now has a red child. And if we look at it, not only do we have a red node that has a red child, but we also have a new red node whose uncle is also black, and we are also the complete right side. We are the right child of a right parent, which means that this whole situation right here is actually going to fall under case 5b, right? This is where kind of the issues with red-black trees kind of pick up, because we need to get all of the information available in order to pick the right case to do the right thing. Right, so in the case of case 5, what we're going to do is we are going to rotate right around the grandparent, right? So we're going to be, our pivot node is going to be up here, right? That's what we're pivoting around, the grandparent. We're rotating left. I apparently have issues with left and right sometimes. Right, so everything's going to shift around this way, and it's going to restructure the tree. So when we shift around that way, because we're rotating left, the grandparent's right child will become the new root. So 2 will become the new root of this subtree. And then 1 is going to become its left child. Right, so he goes down there. And he he's going to have 2 null leaf children. And then 3 will stay as the right child of 2. And then, of course, its 2 subchildren. Okay, so we rotated right, and we see that we are still in violation of Rule 4, though, because we have a red parent with a red child. But, again, in order to fix this, we can go ahead and just recolor things. You could either do with case 5, we swap the grandparents and the parents' color, right? So when we do that, what we're going to end up with is basically, I'll just redraw it, because why not? We go ahead, we'll swap their colors. And I do apologize for how long it takes for me to draw. We have yet to master drawing things on computers. So we swap the colors, so 2 is basically going to become black. And then 1 is going to become red. And of course he would still have this down here. And now, all of a sudden, everything works out perfectly, right? All of our rules are met, and on top of that, the tree is balanced, which is really cool that this just works by doing a simple rotation and changing some colors, right? So now, let's go ahead, we'll move on to the next step, and the next thing we're going to do is we're going to insert 4. And now, in this case, again, I will attempt to copy-paste my tree. Maybe this time it'll be better. There we go. Drag our tree down here. And we'll go ahead and we'll add our 4 in. Which again, remember, our new nodes are always going to be red when we insert them. So we put 4 down here. And then give it its 2 children. Right, and now we can see that, again, when we're running into 4, the new case that we're going to run into is effectively case 3, right? And this case is when both n's parent and uncle are red, right? So in this case, what we want to do is we are just going to simply paint both of the both the parent and uncle black, and then we will paint the grandparent red. Right, so if we do that, one more time. What we're going to end up with is we'll paint him black, and him black, that one, and then we'll paint our grandparent red. And then what we'll find is that we are still in violation of one of our rules, right? Because the root always has to be black, right? Which in this case, it falls under case 1. And there, under case 1, all we have to do is repaint the root node as black, and we're good to go. And then everything should still work out. Yeah, man. Paint you as black. So if we go through and we do all of our black height stuff, we can count to find the distance to any of the leaf nodes. We would go 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Right, so the black height works and the red nodes are all in the correct spot. Right, so this is just a real basic example of how to insert things into a red-black tree. If you wanted more practice, I would highly recommend going through and continuing this pattern. Add 5, add 6, add 7, add 8, etc. And keep following this pattern and all the rules, and you'll see how the tree continues to restructure itself, which is really cool, right? We added 4 sequential numbers to our tree, and we actually resulted in getting an actual balanced tree as we went on. Unlike in a normal binary search tree where we would have instead ended up with something that just looked something like this, right? 1 would go to 2, which would go to 3, which would go to 4. All right, just this linear list that would not provide us any searching benefit at all. Instead, we end up with an actual tree structure, which is useful to us, all without adding, overall complexity-wise or computational complexity, that many more operations. We have a couple rotations, which are just swapping of pointers, so those are constant time, as well as some recolorings, which are also constant time, right? Conceptually, it's very complex, but computationally, it is not. So this is really the big benefit of the red-black trees. Right, so if you're interested in this, keep adding things to this example tree, and keep looking at the rules and seeing how things readjust. And if you have any major questions, make sure to shoot me a message, and I'll try to get those answered for you.